All right, so let's talk about the circuit element models. This is the last section of this class. We're really getting close to the end here. You may have already noticed this, but basically what we've been doing up to this point is we've been transforming the differential equation or equations associated with the circuit into an S-domain equation, which is algebraic. Instead of transforming the differential equation, something else that we can do is we can transform the circuit itself, which means like element-wise, we can take each component and transform it into its S-domain equivalent. So instead of a time-varying function of voltage, we can get an S-domain function for our voltage. Instead of an inductor in the time domain, we can get an inductor in the S-domain, and we can even take that initial condition into account. And the same goes for the capacitors and the resistors. And so you may have already noticed this. Remember when we did phasors and everything, we would say that the impedance in the frequency domain for an inductor was j omega L. And then we also said at some point that we can assume S is equal to j omega when we're doing frequency response. Well, now you can see that S is part of the S-domain equivalent for an inductor. So you could kind of see here that I could say that this is j omega L. Of course, when we're actually in the S-domain, we can't say S is equal to j omega because it's S is equal to sigma plus j omega. When we're doing frequency response, we just assume sigma is 0. Okay, but you can kind of see the same pattern as when we were doing phasors, where this is SL for the inductor. It was j omega L when we did phasors. This is 1 over SC for the capacitor. It was 1 over j omega C when we did phasors, etc. Okay, and so there's some familiarity here. The difference is that we have to add these initial condition terms. Of course, if the initial condition for this voltage is 0, then it's just an inductor, and we don't have to think about this. And if the initial condition for the capacitor is 0, then it's just a capacitor, and this portion is completely cut out, so we don't have to think about that. But they do allow for the possibility of modeling these initial conditions. And so I'm going to go ahead and end this video here. Again, it's not the same thing as saying j omega L because we're not doing frequency response. This is completely different, but it looks similar and it's familiar because when we were doing the transformation into the phasor domain, we were basically saying we're going to assume that our impedance is S times L, but we're letting S equal sigma plus j omega when sigma is equal to 0, which is why this eventually just became j omega L. And so now we're doing the same thing, except we're not assuming sigma is 0, so we just write it as S times L for the S-domain expression for the inductor, and similarly for the capacitor. Okay, so this is what we're going to be doing. We're basically going to look at how we can model resistors, how we can model inductors, and how we can model capacitors in the S-domain. We will redo 2 more examples at the end here using initial conditions, since we already did 2 examples that don't. And then we'll be done. We'll be done with EE221 material. So let's go ahead and end this video, and we'll get into how to model these elements in the next couple videos.